So for this one, we're just taking the volume of the big cylinder, which ends up being pi times 5 squared times 2, minus the volume of the small one, to find the volume of that whole solid. Right? Big minus the small. And we end up getting 32 pi inches cubed. That kind of leads us into what we're doing today, because the volumes that we're going to deal with today, they're not solid cylinders when we spin them around. Right, yesterday we looked at discs where we had a solid cylinder, which we call the disc, to find the volume of an odd looking shape. But now, if we look at this graph, we've done some problems where we had to find the area between two curves like this. But now we're taking that whole shape and rotating around the x-axis. And what happens, and it may be a little hard to see here, but what happens is there's a hole in the middle. Right? There's a hole in the middle. So if we look at this, looking at a rectangle here, we'd have like a little dx cut. If we spin that rectangle around, what happens is we end up getting a washer. Right? This cylinder with a hole in it. So we're not always going to have solid cylinders that make up this solid of revolution. So sometimes there's going to be a hole, and that's what we're dealing with today. So this is kind of our second technique in finding volume. There's one more we'll talk about later. But for this, let's look at this example. If we were to try and find the volume of this whole shape, I know it's kind of cut off, but if this was complete, basically we're doing what we did in that problem up above. We're taking the volume of the big shape minus the volume of the small shape. Alright, so we're taking the volume of the big minus the volume of the small. And then we get what's left over. Well, the volume of the big one, we'd have the definite integral from a to b. We're doing pi, which can go on the outside or inside, times the radius squared times the height. Well, we know the height's going to be dx, right? That's always dx or dy for the problems that we're doing. The radius for the big one would be f of x, right? That's the function that's furthest away from the axis of revolution. If we look at this washer, our big radius goes from the axis of revolution, the x-axis, all the way up to the top of that graph. And the top of that graph is y equals f of x. So we'd have f of x squared times our height, which is dx. Minus the volume of the small one, we're going to have pi times definite integral from a to b. And the radius of the small part, I should have wrote this with a big R here. Radius of the small part goes from the x-axis up to the bottom of this region, which is the graph y equals g of x. So we're going to have g of x squared for our radius squared, and then our height again is dx. But we can actually combine those, since those will both have definite integrals from a to b, we can combine that into one definite integral. Pi times the definite integral from a to b of f of x squared minus g of x squared dx. Right, because these have some things in common, the pi's, the dx. We can combine that into one definite integral. But the way I like to kind of think of this or remember this formula is a little bit different. I think of it as pi times definite integral from a to b of this f of x represents the big radius squared minus the little radius squared, and then times the height. So I'm not going to put dx because the height could be dx or dy. And so the height's always going to be dx or dy, one of the two depending on the situation.